Hi, I'm Greg Humphrey.
My name is Brandon Saplicki.
I'm Cole Roberts.
I'm Nick DePalma. We're Team Grus, and our Capstone project is Cloud Sensing, a cloud-based sensing platform for the Internet of Things.
The purpose of this project is to model the Internet of Things. The Internet of Things is the idea of widespread interconnectivity between all electronic devices. This application of highly integrated computers can lead to less waste and loss in general society, with these computers providing humanity with a better way of collecting information. We want to provide a powerful sensing platform for sensing service consumers to acquire environment data based on sensing service providers and the physical sensing resources provided by the sensor owners. We can accomplish this by having sensor modules capture data and push it to a cloud server that can be accessed by a web portal.
The system we are modeling implements an efficient relay of information, as shown by this architecture diagram. The WASP mode sensors are first programmed and dispersed in the desired environment ready to collect and transmit data. The data collected is transferred through a preset gateway en route to the designated cloud storage. The data is then accessible to users via web browser or mobile application.
There are three distinct parts to our project, and each utilizes a different set of tools and technologies. For the simulation of the sensor nodes and varying network topologies, OMNet++ was utilized. OMNet++ is an open-source, component-based simulation engine built on C++ foundations. The Mimics modeling framework was used on top of OMNet++ to ease in the creation of the actual network models. For the collection of data, hardware sensor nodes called WASP modes were implemented. The WASP mode is an Arduino-based platform that allows for customization of the data that is collected through the use of various add-on sensor boards. These sensors can capture environmental data such as temperature, humidity, and others, as well as capture images and video. All of this information can be sent to the cloud network through the network technologies such as Zigbee, 3G, and Wi-Fi to be accessed by the website for display. Finally, for presenting the data that has been collected in the cloud, a Java-based website was created. The website utilizes the Vaadin 7 framework, which is designed for creating rich and interactive applications that run in the browser without any need for plugins. Through this website, users will be able to gain access to the data that they need in a user-friendly fashion.
The simulation results shown here display a network of nodes that are dynamically created and then send burst messages to each other to be forwarded to the base station. The node checks itself to see if there are any messages waiting to be sent, and then it forwards them down the line to the base station. The results of those messages are then displayed on the right-hand side. We first turn on the WASP mode sensor module to start the process of taking a picture to be sent to the website. First, the WASP mode starts up its 3G and Wi-Fi boards. Now the WASP mode starts to take a picture that can then be sent via FTP to our website server. The FTP process has begun on the WASP mode side, and the server on the website should now be receiving our picture that the WASP mode took at roughly 700 bytes per second. You can see that image.jpg is now being transferred over to the server. We now log into the website using admin credentials to access the WASP mode data, specifically the picture we just took. As we open up the consumer services, we can now see the picture that we took moments earlier displayed on our website.
As a team, we learned a variety of lessons throughout this project. Some of these lessons learned included time management and project planning. Each team member had various responsibilities and commitments outside of school, which made scheduling difficult. Through using calendars effectively and the use of online collaboration tools, we were able to overcome this. Along with the learning curve of using new software, we experienced many issues and bugs which limited functionality. After contacting the developers and using their forums repeatedly, we were able to remedy many of the issues. This project, being multifaceted, required excellent communication between team members. All forms of communication were used, including phone, text, email, and chat. There is a difference between being taught how to work cohesively and actually doing it. We as a team at the end of the project have achieved this.
In conclusion, we consider our efforts a success because we were able to simulate an Internet of Things network in OmNet++, implement photo capture functionality into the WASP modes, create a working website to hold user and WASP mode data, and finally integrate everything into a cohesive project, taking a picture and sending it via FTP to our website server to be displayed.
We'd like to thank Jay, the graduate student assigned to this project, for meeting with us multiple times a week and supplying us with a prototype.
We'd also like to thank Dr. Dijang Huang, who made this project available to us.
We'd also like to thank the hundreds of Google posts and forum posts that we visited in order to make the project a success.
And we'd like to thank Dr. Deborah Callis for all her help and support these past 2 semesters.